What do you think is the greatest challenge against humanity to explore the vast expanse beyond Earth? The vacuum of space, long-term isolation, or perhaps radiation exposure? While all of these play a part, one of the most critical challenges is the inadequacy of astronauts' physical strength to carry out manual tasks in low-gravity environments.
According to NASA, dwelling in a microgravity environment causes astronauts to lose bone density by 1% every month and experience muscle atrophy by 20% to 30% after returning to the Earth. While astronauts already encounter physical weakening, the bulky structured spacesuits also create another challenge. The EMUs that are commonly used spacesuits astronauts wear while performing their out-of-spacecraft tasks are essential for protection. However, they are inflexible and inconvenient for precise movements, making it difficult to complete tasks successfully.
It all began when we watched the Avatar movie in one of our school book club meetings. The magnificent robot character named Beyond Glory caught our attention and filled our minds with the idea of utilizing the exoskeleton technology for creating a change. Thus, as Guardians in Suez team of 5 dedicated students, we were ready to develop our solution, Celestron.
Celestron is an exoskeleton subsuit designed for physical strength augmentation and simplified exercising in space. We can categorize the components of Celestron into 3 parts: mainframe, technical compartments, and coating. In the mainframe, we use 3 types of motors: step motor, rotational motor, and servo motor. Step motors drive our custom-designed artificial muscles, which combine rope, vinyl tubing, and steel rods for strength and flexibility. Servo motors, on the other hand, pull the ropes that power the hand exoskeleton, enabling precise finger movements. Meanwhile, rotational motors handle the joints, ensuring smooth and natural motions.
The technical compartments involve EMGs for sensing muscle movement and conveying the signals to the relevant motor by Arduino, and string arch for calculating the joint torque and activating motors accordingly. For energy supply, we choose lithium-ion battery, which is the most appropriate for space conditions. Last but not least, the coating part is essential to protect the electronics and to form the mechanical structure properly. The outer structure is made of carbon fiber, a highly durable material, and spandex as a material for connecting the outer parts of the exoskeleton.
So, how do all this work? We detect the intention to move via EMG sensors before the motion occurs. Data from the EMG sensor is processed in Arduino, which monitors the analog data from EMG sensors and sets threshold minimum and maximum values of muscle contraction calculated by the EMG. When the received sensor value falls below the minimum threshold, step motor will coil the cables, muscle relaxation occurs and elbow extends, whereas when the received sensor value exceeds the maximum threshold, muscle contraction occurs and the elbow flexes. Celestron adjusts the support torque according to the joint torque, generating a piecewise function relationship where the input value is joint torque and the output value is the step motor's angular speed. To change the speed of step motors, we use a gearbox. The same correlation is also operated for the resistance mode, where Celestron adjusts the resistance against the motion applied by artificial muscles.
GIS will first enter the medical technology market and then space technology market, targeting 2 customer needs: ensuring astronaut safety and efficiency in space missions, and advancing rehabilitation processes in healthcare. Considering these factors, we defined our customer personas as given here. We will enter the medical technology market in 2025 and target a 0.5 to 1% market share. In 2028, we plan to move to the space sector and increase this ratio to 3 to 5%.
To develop our product, we identified the key competing factors of present exoskeletons, including expensiveness, accessibility, and complex control. Through our strategic canvas analysis, we compared these factors to existing markets and pinpointed critical areas for improvement.
Current solutions often lack affordability, limiting accessibility to only a few industries. Additionally, their multifunctionality and innovativeness are constrained by complex control systems, making them challenging to use for our target customers. By addressing these limitations, we aim to outperform existing models and expand accessibility to a broader range of professionals, ranging from operating in extreme conditions to healthcare services. Celestron stands out with lightweight modular design and affordable yet durable materials. Unlike conventional models, it offers rapid adaptability to different terrains, easy integration with wearable tech, and enhanced mobility with minimal energy consumption.